Hey Percy, how are you? Well, it seems like you're ready for the test. Hmm? Well, it looks like you're ready for the test. So when's your test? Monday, okay. So Friday is a good time, I think. I will do my best, I promise. But I don't think I can. So do you have any questions regarding any homeworks problem? I see, I see. So just let you know, so the YouTube live is going to have a delay in it. Like last time it was really bad. It was like 30-second delay. So please, if you have any questions, just use Discord to ask me. Whew. Oh wait, so I have a question for you. You're a VIP? Because of what? Ah, I see that. It's definitely a dodge. Yeah, Madansh is in control of the Discord. Ooh, I hope more people join the Discord. Because if... Yeah, because... Well, because I need people to ask me questions. Or the review is going to be really short because I have never taken Basu before. Just trust me on this. People are going to begin leaving. Can you hear me okay though? Hello? Okay, great. That's great. So I'm thinking about starting at 7:10, just so people can see the Discord announcement and see if they want to join. If that's okay. Yeah. That's a good idea. So let me put it on the slide then. So Yeah. How come? What is this thing? I have no idea. Chat. Okay, let me see. How do I go back? Channel is locked. What does that mean? Okay, let me check with Badansh. Okay, they're checking right now. Yeah, is it for the Discord channel? Oh, we have more people now. That's great. Jeremy, they're going to need your better log skill. That's weird. I don't know, they're saying the Discord channel is locked. I think I'm... Yeah. Maybe I gave them the wrong address. Okay. Okay. Yeah, that should be fine. But the problem is, I'm going to get a really big delay. Hi everyone. So before we start, I want to welcome you to join the Discord server where you can share your screen and ask me questions if you can. So before we start, is there any specific questions you want me to cover? So I got a question saying how can we convert the 16 to 1 mux into a 2 to 1 mux? Okay, that's going to be pretty easy. So first I'm going to talk about the sum of product and product of sum first, and after that the mux should be near the end of this test review, just to keep everything in order. But if everyone is comfortable with POS and SOP and Kmaps, those kind of stuff, then we can move to the more complicated problem. Does anyone want me to cover SOP or POS? A POS Kmap. Okay, so let me start. Can everyone see my screen? Okay, great. So, give me a second. Sorry about that. So let me start with the Kmap. So for example, we have an equation that's f, and let's say w, x, y, z. We know that this will go from MSB to LSB. And let's say, according to the example, we have 0, 1, 2, 10, and 12. So then we can convert this table, this fluid equation, into the Kmap form. Let's see. So in order to fit this Kmap according to our MSB and LSB, so we know that for these cells here, we have from 0 to 3, which means the most significant bit, Wx, is on top. So we can write it as W0 and W, and this will be X, X0. And for this portion here, we can write it as Y, not Y, and this part will be C, Z0. Does anyone has any question about how I label this? Okay, so then let's move on. So we know that according to this form, we have a sum of min term. So that means we have to fill 1 for each corresponding number. So we have 1 at 0 because of this term, and 1 at this one. For 2, we have 1 at this one. 3, 4, 7, 9, 10, and 12. And the rest we will just fill 0 because there are no don't cares. So for POS, we want to look at the 0 here instead of the 1. So how do we group this? We group this 2 together, this 2, these 2, and this one is just by itself. So since if we're looking at 1, we want to write the function as f, and we are looking at 0 in this case, so we have to write f naught. So f naught equals to, say, so for this one here, w is changing here, so which means we are left with x and y naught and z. And this one is changing here. W is not changing. So we have y naught. Sorry about this. It's y. Y and z. And the next one we have this loop here, which we write x, y, and z naught. And the last one is by itself, so there's no way to simplify it, so we write it as w w x naught, y naught, and z naught. So we're trying to find the function of f. So in order to turn this into this, we have to invert the f naught, right? So we have to invert the entire Boolean equation. And f naught just become f naught, f. So we can apply De Morgan's theorem, break the line here, and then we will get x, y naught, z. W, y, z, x, y, z naught, w, x naught, y naught, z naught. In the next step, we have to do the inner line here, break the line, change the sign, so we have x naught or x, y naught, or z naught, ended with w naught or y naught or z naught, x naught, y naught, z naught. And for the last one we have w naught, x naught, y naught, and z naught. And we all know that double invert is just equal to the variable without the invert. So this is how we get POS from the SOM function. Is there any question? So I got a question saying, can I make a group of 6 minterms together? No, we cannot. It has to be 2 to the n. So that means we can only group 1, 2, 4, 8, and so on, right? Anyone has any questions? All good? Okay, so the next part, let's talk about the standard form of SOP and the POS. So we know that this is a simplified version. But what if we want the most complicated version? Let's take SOP as an example first. We have, let's say, A, B, C. Sum of minterm. We have 0, 1, 2, 4, and let's say 7. So how do we simplify this? We want to draw a Kmap. This is the 3-variable one. Let's put the MSB AB here and C here. So C0, C. Okay, so we put 1 here and 3, 4, 7. So in order to simplify this sum of minterm function into SOP, we can group, say, these two first. So we got F equals to, so we know that this term is changing, the A term is changing, so we have to keep the B0, right? So then next one is C0, that's not changing. And, oh, sorry. Now we can move on to the next loop. We can group these two together. So we will have A0, because A0 is not changing. So A0, C. And the last loop is this one. We have B, C. So we know this is the most simplified version, and how are we going to change this to C SOP? We have to do the expansion, right? So F equal to B0, C0, A or A0, or it with A0, C. B is missing in this term, so B or B0, or BC, A or A0. So applying the distribution, law, we can get A, B naught, C naught, or A naught, B naught, C naught. Is this clear? Anyone has any questions? Okay, let's move on. And how about CPOS? So let's do the method we did to find the simplified POS. So we want to group these two together. So we can write it as F naught, because we're looking at the 0, equals to B, because B is not changing, and C naught. Or this one is just by itself, so we will get A, B naught, C. So then we have to invert F to get F. So we will have BC invert ended with AB naught C invert. Then further on we will get B naught or C double naught, A naught or B double naught or C naught, right? So we will get B or C, B naught or C, ended with A naught or B or C naught. So this is our simplified version of POS. And in order to find CPOS, we had to find the missing term. In this case, this one is missing A, and this one is not missing anything. So we can write it as A naught ended with A, or B naught or C, and this one stays the same. And in order to get this one to POS again, we have to do, there's a law for that. It's, give me a second. So we know that A or B and C will give you a property. This is a property. That's A or B, A or C, right? So by applying this property, we can get B naught or C or A naught, B naught or C or A, and then this term stay the same, C naught. Does this part make sense? And if I make any mistake, please stop me. This is your CPOS form. Okay, then let's move on to the next topic. Is everyone comfortable with 5-variable Kmap? Does anyone want me to go through the problem? Anyone? Any questions? So the next part will be gate equivalency. So let's say we have a NAND gate. And in order to make this into an inverter, we can simply connect both of the input together. And this will get us an inverter. And same thing for the NOR gate. So let's try to realize the function above this one. Let's say we have this one for example. And how do we convert it to NAND or NOR? So we first double invert the entire thing. Double invert. And this will become, by applying the De Morgan's theorem, this will become B naught C naught naught ended with A naught C ended with BC naught. So we know that we have, here is the 3 input NAND. And inside each individual terms, we have 2 terms. So we have 2 input NAND. And for the individual invert here, this will be our inverter. So let's say, because in this case we have 3 individual bars, so we have 3 inverter. So from this we can know for sure A, B, C. We have signals from A, B, and C. And let's use a NAND gate. So this will be our inverter for A. This will be for B. And this will be for C. Now looking at this term, B naught, C naught is NANDed together. So we can use 2 input NAND gate and connect this point and this one to this. So we can write it as C naught, B naught, C naught, invert here. And the next term we have is A naught C and a NAND. So we can write this as A naught C from here, non-inverted. The last term is B, C, NAND. B is not inverted, so we choose this wire here. And C is also not inverted, so this one here. And then we can look at the final gate, which is a 3D input NAND. You can simply draw this as this 3D input NAND gate. And this will be our F. Is this clear? Any questions? All good? Okay. So I know from one problem of your homework, we're going to compare two functions and see if they are equal, right? And one is SOP and one is POS. So then we can start from the top portion, let's say. Actually, we should start from here. So we know we have our POS function here. And how are we going to know the POS equals to this one? So we know F equal to B naught or C, A naught or B, or C naught. F2 is our SOP, which is, let's see, B naught, C naught, A naught, C, or BC. So how do we know F1 equal to F2? Assuming we didn't find this from the Kmap. So we want to convert this function here into F1 naught first. So we will get the Morgan's theorem for this is B naught or C invert, or A naught or B or C invert. And from this we will get B naught naught, C naught, or A naught naught, B naught, or C naught. Oh, sorry about this. It's not or, it's and it together. B naught, C naught. So we know double invert cancels. So B, C naught, or A, B naught, C naught. And then we know F2 is B naught, C naught plus A naught C plus BC. And I think an easier way to do this is we can fill in the Kmap for this. So let's start from F1 first. Say A, B here. So C naught, C. And how do we do this? This is your A naught, B naught, A naught B, A B, A B naught. So we know that we have B C naught, which means A is your don't care. So in this case, we're just going to fill this. B C naught is this two cells. So 0 0. Because this is F naught, so we want to fill out as 0 0. And we have the next term is A B naught C naught. A B naught C naught. So it's this one, right? Wait, this looks wrong. This is. Did I forget something? So B naught C naught. Oh, sorry, I forgot the C naught here. So this one here should be C naught. Sorry. And when we double invert C naught, we will get C. Instead of C naught. So this is not 0. The 0 should be here. And then the rest will be 1 because we filled in the F naught portion. And when looking at this function, we can create another truth table. C naught C. A naught B naught. A naught B. A B. A B naught. So the first term is BC. B naught C naught. So we want to find the term that B is not. And so since A is not in this term, so we can put 1 here and 1 here. And in this term, B is not in there. So we just need to make sure A is not. So this one and this one. And C. So we know we have to put 1 here. For this term, A is not in there. So it can either be A naught and A. So we just need to make sure B is not inverted and C is not inverted. So we can see this is the last one. So fill in the 0 here. And as you can see, these two Kmaps are equal. Any questions? Yeah, so for conclusion, we can say that F1 equals to F2. the next part. Then we should do some word problems. Let's say we have a light room, and the light can be controlled by 2 switches. We know that if we toggle a light and the light is on, then the other switch, if we toggle the other switch, the light will become off. And from the truth table, let's say switch X and Y. And let's say F is whether the light is on or not. So F equals 1 equals is that the light's on. F equals to 0 is light off. So we can first start with a truth table. XY 0 0 0 1 1 0 1 1. So we know for switch X, this is on, this is off, this is on, and this is off. If both switches are off, then we can assume that F is 0, right? And if Y is on, if we turn the switch, toggle the switch Y and then move it to position on, we know F is 1. And as you can see, this is 1. And the last one, assuming that we toggle X first. We toggle X first, and then the light turn on. What happens if we toggle the other switch that's to the on position? The light in the room will actually turn off, right? So F equals to 0. So in this case, this will be 0, right? And according to the truth table we have here, we don't even need to do any complicated. We don't need to do X, Y naught or X naught Y. We can already tell that this will be XOR, right? Which is this logic gate here. Does this part make sense? Okay. Does anyone has any question regarding the Kmap key? No? So how about the decoders? So we know a decoder circuit is as follow. Let's say we have XY let's say, if we have inputs XY, how many outputs will we have? We will have 1 output, 2 outputs, 3 outputs, and 4 outputs, right? So let's say we have F3, F2, F1, and F0. This is the definition of decoder. If X, Y are both 0, then we will activate the output F0 here and use it as 1. So the rest will be 0. And likewise, for if X is 0, Y is 1, this will be 0, 0, 1, 0. And if X is 1, this will be 0, 1, 0, 0. And the last one will be at F3. This is a definition for decoder. Then we can draw the circuit here. X, Y. Let's invert this. So for the first one, we have Y0 and X0. This is your F0. And for this one here, F1, we have X0, Y. So we can say X0 and Y. For this one, this will be our F1. And for F2, we have X, Y0. Y0. So this is your F2. And then the last one is just XY. And normally, if the problem is not asking you to draw the internal circuit of the decoder, we can just write it like this. In this case, it's 2 by 4, right? So decoder 2 by 4. 2 inputs. I have 4 outputs. 0, 1, 2, 3. 0, 1. And LSB, MSB. So will be LSB, MSB. Any questions? I assume there's no question for this one. And an encoder is the opposite, right? The opposite of decoder. So let's say we have input, And because we have 4 and 2 to the first, so we have 0 0 0 1 1 0 1 1. So we have for variables, for I mean not for variables, for output, I mean for inputs for this one. And let's say we have x, we have f1 and f0. We fill in the diagonal, so 0 0 0 1 0 0 1 0 0 1 0 0 1 0 0 0. And for the first one, we define it as 0 0. And the second one, we will define it as 0 1. Next one is 1 0 and 1 1. So this is the definition of decoder, encoder. So for F, we know we have I3 not, I2, I1 not, I0 not, or I3, I2, I1 not. For F0, we have I3 not, I2 not, I1, I0 not, or same one with I2 not. So the internal circuit of the encoder can be realized by using this two function. So we have I3 and 4 input AND gate. And let's just use the small invert here to represent this. So I3 not with I2 with I1 not and I0 not. And OR with the other 4 inputs and gate. In this case, we have I3, I2 invert, I1 invert, I0 invert. So we know this is F1. And now we're left with F0. So for the first one, we have I3 invert, I2 invert, I1 stays the same, so I0 invert. So connect the line. And so there's another OR gate, and this will be F0. And if you notice this function here is the same as this one, which is this NAND gate. So that means we can directly use the gate we already created and connect here. Any question? So we have two outputs, F1 and F0. This is 4x2 encoder. And should I move on to multiplexer? So we know that one person asked how to turn 16 to 1 into a 2 by 1 multiplexer, right? But before we go on to that part, let's start with how the multiplexer work. So we have this. Let's say if we have two inputs, we will only have one selectors, right? Because the selectors are going to just select which input to go through the output. This is F. So if S0 is 0, and this input, let's say we input an X at address 0, and S0 is 0, so we know F equals to X S0 naught. And if we input a 1 into a selector, and let's say this is Y, we will pass Y to F when S0 is 1. So, or with Y S0. And if we want to realize the internal circuit, we can do so by using this function here. X input and selectors. X connected to the first AND gate. And since S0 is invert, so we do this. And the next one is non-inverted. Y S0, X S0 naught. And this will order together. So this is your F. And we apply the same concept for 4 by 1 mux, which is 1, 2, 3. So these are our inputs. So because we have 4 inputs to select to pass through the output, we will have 2 selectors. Because 0, 0, 0, 1, 1, 0, and 1, 1. And this will be your F. So someone asked the question how to change the 16 to 1 into a 2 to 1, right? There's a couple of ways to do this. So first we have, this box 0, 1, 2. So how many selectors will we have? We will have 4, right? That's correct. So S3. This is F. So if we're converting the larger inputs to a smaller input, we want to look at the MSB selectors here. What happens if we input a 1 to S3? If we input a 1, because 1, 0, 0, 0 equals to 8, right? So we have to start from 8, and the rest doesn't matter. The rest of the input doesn't matter. We can connect all the input here together. To Y. Let's say the input is Y. And if the MSB selector is 0, then we look at the address that's less than 8. And connect them together. And let's say this is X. So this is equal to this one. Does this make sense? If we use S3 as our selectors for the 2 input, then we don't have to worry about the rest of these input. This can be either ground or 1, it doesn't matter, as long as you are in control of S3. And we can also say that using a 16:1, and what if we want to select S0 to use instead of S3? We know S0, when S0 is 0, it will select this one. It can also select this one, all the even number, right? So we have to make sure this is inputted as 0. Give me a second. So if we use S0 as our selectors, and when it's 0, then we can say this is, let's say we input the X in here, and when S0 is 1, we want this to input here, and the input here doesn't matter, but we just have to make sure that S3, S2, and S1 are all grounded, which is active low, so it doesn't interfere with your other addresses. Does this make sense? Okay, great. So as we can see that we better use S3, right? If we use S3 here and this is 0, and it doesn't matter whether these 3 are 0 or 1. If we connect all the value below 8 and say this is X, this will always be F equals to X S3 naught. and use 1. Count at only 8 inputs, so this will all be y is 3. And now to the demux. We know that demux is just the opposite of mux. We have 1 input, and let's say we have 2 outputs, F0, F1. How many selectors do we need? 1, right. So we have 1 input here. And if the selector is 0, then this output address will output I0. And F1 will be 0. And if S0 is 1, then it's the opposite, which means I0 goes to F1 and 0 goes to F0. So applying the same concept, we can derive other muxes, demuxes, which is 1 to 4 or 1 to 8. Any question? Okay, great. So let's say do you want me to cover LUT? Or tri-state? Anyone? So LUT is a bit similar to ROM. LUT lookup tables. And if I'm wrong, correct me, because I'm not familiar with this, but are you okay with LUT? Okay. How about tri-state? Okay, I guess. Okay, sorry. So let's say LUT will have 1 bit address. So let's say we have 2 inputs, X, Y, and together. Actually, let's find the circuit above and see how we're going to convert it to. Okay, similar to this one. Let's say we have X, Y, and Z. And X is ended with Y. Why not, actually? Let's do why not. And Z is then board to produce an output of F. So let's do 2 inputs LUT. So let's say this is X, Y, and let's say this is MSB, LSB. So at address 0, which is X naught, Y naught. We know the function outputted here is X and Y naught, right? So that means at address 1, 0, 1, 0 is 2, address 2, so 1, 2, and last one is 3. So this will be, we will assign this 1, and the rest will be 0. And from here we know that if we input 0 and 0 into XY, we will get the output of this address, which is 0. But if we input a 1, 0 into XY, 1, 0 in binary into decimal is 2, so we will select this address and pass to the output, so this will be 1. So now let's take care of the C. We first want to draw a truth table here, and F 0, 0, 0, 0, 0, 1. Actually, I think I have that. Okay, this one. Sorry about this. Okay. Great. Well. What? Sorry, give me a second. Okay. Let's say this is X, Y, and Z. And according to the circuit above, whenever Z is 1, we already know this will be 1, right? So this is 1, 1, 1, and 1. So whenever X, Y are 1, 0, the AND gate will output 1 to the OR gate. So then we can say whenever X, Y are 1, 0, the output will be 1 as well, which is the truth table here. The rest are 0. And from this LUT here, we already have a output. Let's say this is D. So from this truth table, we can simplify the truth table into 2 input, D and C. So 0 0 0 1 1 0 1 1, and this will be our f. So we know whenever d is 1, the f will be 1 according to the truth table here, and whenever z is 1, f will also be 1 as well. So this will be the truth table here, and we can write it according to this and say f equals to d naught c, or d c naught, or dz. So let's make another LUT. This is 2 input still, because we have d and c, and let's input d here, meaning this output goes to the second LUT input, MSB, and z will be this one. So we know whenever dz are 1, and this one will be 2 and 3, f will output a 1, right? So let's say we have the output from LUT is f. Then we have address 0, 1, 2, 3. And to number this, we just have to look at this truth table here. At address 0, we have 0 here. Address 1, 2, 3, we all have 1. So this LUT function is equivalent to x, y naught, or z. Does this make sense? Yes, okay, great. And anyone has any question? If not, then I think I will go over Verilog first. And then for the rest of the time, till 9 o'clock, I will be answering any question you have. Okay, so let's go over Verilog. And I think your professor is just going to ask you to explain the code. He is probably not going to ask you to build one. So let's say this is working. Okay. So this is a simple Verilog program. Let me enlarge this. Okay, so only explain, that's great. So we have a module here, and this module is OR gate, and we have an input AB of AB, and this is our output. And we first define the parameter here, and for whether the variable is input or output, we're defining in the body of the module. So input, we select the A and B here, and the output we named it as C. So then we can assign C equals to A input or B input, and this one is your OR function, and this is pretty simple. And for AND gate, we can write it as, let's name this as AND gate. AND gate. And the function for AND is simply this one, an AND symbol. So we're assigning the output to be equal to A input ANDed with B input. Is there any questions so far? Okay, so if there's no question, then we can move on to the test bench. So for test bench, we're basically making a truth table for our program, UUT program here. And so we just set A from 0, 0 here. And this is called the delay. Let me enlarge this program. So we have module and register A and B. Because this is test bench, we wanted to store into the register. And the wire C is just our output. And this is just how we would define the input output here. And initial begin, we can then begin our testing process. And first, we assigned A equals to 0 and B equals to 0. And then we assign a delay. And you will see why we need a delay later. This is 100 nanosecond. And first, we start as AB equals to 0, 0, delay of 100 nanosecond, and AB as 0, 1, 100 nanosecond, and A is assigned as 1, and this one should be B. Sorry, a typo here. 1, 0. And the next, last test statement is just 1, 1. And if we run this code, run this test bench, let's see. Okay, and then we can click the fit to Windows here. So we'll first start with A 0, 0, 100 second delay, and then this is still 0, 0. And this is going this is setting B to 1 now, and which is 0, 1. As you can see, this is the OR gate, so we have the output C as 1. And the next state here we have A as 1 and B as 0. So this is our next test statement. And as you can see here, C is still 1. And the rest are just both A and B are 1. So this is the simple Verilog program. We can move to the more complicated one, which is this, the OR gate. Okay, so this one is the mux. Let me see. Oh, this is the adder. Have your professor go through adder yet? Okay, so let's skip this part. But I would like to explain the structure of the adder first, because you don't need to understand it, but I'm sure you will understand the code better if I explain the structure. So this is your full adder circuit. It's given to you, and let's assume you're asked to design this problem in Verilog. So we can get. So this function is your XOR, and the other one you have seen is AND and OR. And from this we can simply put a temporary variable for, in this case, your output here. This is your output, and looking at this part. In this case I have X, Y, so let's change this to A, B. Okay, so, and we have to change everything inside the perimeter, so A, B. So we're defining A, B, and C in as our input, just like the circuit shown here. And we continue to change X equals to A, Y to B, so B, A, and Y. And this C in, C out. Okay, so right now, the first statement here, sign here, is our output of the XOR gate. And then the second one, we're setting sum equals to Cin XOR it with temporary one. And temporary one is the output of A XOR B. So the next one is for the AND gate, which we're, let me erase this. So we have temp2, and temp2 is temp1 ended with Cin. So this is temp2. Temp1, I mean. So temp1 ended with AND gate, and Cin ended with temp1. So this is our function here. And this will be, we assign this as our temp2. And the next AND gate, the next AND gate is A and B. As you can see here, A is ended with B. And we assign this as temp3. The last statement, C out, we're assigning C out to be temp2 or it with temp3. So this is how you're going to convert the circuit into Verilog. Is there any question? Makes sense? Okay, great. All good. And let's move on. This is our multiplexer. I believe one of your homework problems has to do with designing a multiplexer in Verilog, right? So this is a pretty simple concept as well. So in this case, we're setting X, Y, and Z here as our selectors. So to make this easier, let's say we have S3, S2, and S1. Well, maybe I should do this, S0, S1, and S2. So W will be your input to the mux. And this is your output. We define F as output. And so since F is output, we usually set a register for that variable. So now this always here, what does this mean? This is basically a statement. It's more like a loop. And whenever, always add the parentheses, whenever one of the variable here changes value, always will begin running through the content inside. So let's say W, X, Y, Z, or F changes from 0 to 1, and then this always will pick up the signal and begin running through each statement. So first, let me change this to S2, S2, S1, S0. S2, S0. Sorry, this is going to take a long time. Okay, so for the first statement here, the if statement, we're selecting the address at 111, which is 7. Yes, 7, right? So let me write down the function for this whiteboard. No. So we're setting we know that we have 3 selectors, S0, S1, S2. So how many inputs do we have? Eight, right? So we have 0, 1, 2, 3, 4, 5, 6, 7. So assuming that this is already given as we can then derive the circuit from the code here. So we know at address 111, which is 7, right? 7, this one here. We're assigning W0. This symbol here is the function for not. So we will get W0 input into this one. So the next one is 110. So S2. So 110 is at address 6. So at address 6, we will have W0 again. How about address 101? What's the input at address 5? Any idea? Because for the if statement, we're checking if, yes, W, right? Because as selectors, if selectors equals to 101 at address 5, this will be W. F will equals to W. So the next one is 100, which is 4. And this one will be, what's the input for this one? 0. And we can then follow the same concept. So this will be W0, right? And W, and 1, and W0. So this is how we can create a circuit, physical circuit from the Verilog code here. Now moving on to the test bench. Before I move on, is there anyone has any question? Okay. How about other people? Oh, good. That's great. So let's move on to the test bench. And for test bench, we basically do the same thing. We want to loop through every possible input, so which is following the truth table. And in this case, we know we have W, X, Y, Z, right? And I should change this to, I need to change this to S2, S1, S0 as well. And this one is the, you can say this is an array, something. So we know this is 4 to 0. So this is for the for loop here. If we don't define this statement here, we will not be able to use the for loop to assign value to W, X, Y, Z. Let's say this is S2. I will explain further what this means once I finish this. So we know that we have four inputs, W, S2, S1, and S0, right? And it's going to be really troublesome if we are just going to assign each to from 0, 0, 0 and to 1, 1, 1, 1, right? And can somebody tell me what's the maximum value at 1, 1, 1, 1 in decimal? Right, so we will get A plus 4 plus 2 plus 1, right? So this will be 15, like Coleman said. And so this function here is going to define the upper bound, and this is the lower bound. So we start at 0, and this should be 15, right? And each time the loop, I'm sure a lot of you are familiar with for loop, right? So we have to begin the for loop and assigning decimal value. When I equals to 0, we assign into this for variable, and W is our MSB and S0 is our LSB. So if we do this statement, W, S2, S1, S0, and if we do this 0, then we will get 0, 0, 0, 0 to be assigned into each variable. And likewise, if we do like set 10, we will have 1, 0, 1, 0, right? Is everyone following? Okay, so basically this loop is assigning from 0, 0, 0, 0 to 0, 0, 0, 0 to 1, 1, 1, 1. And don't forget we have to add a delay here so we can see the output waveform. So then we can start running the test bench. Have you started coding in Verilog yet? Or are you just explaining? Oh, what happened? Oh, sorry. So because I changed the variable from X to S2, so we have to change this value. Oh, this is still W. And this will be S2. This will be S1. And the last one is S0. And F remains the same. And let's test this again. Let's move this here and look at the circuit here. So for the first one, we have had address 0, 0, 0, and it's going to, according to the circuit here, it's going to output W naught, right? And in this case, W is 0, so the inverse of 0 is 1. So as you can see here, our output is 1 for F. And the next one is 0, 0, 1 at address 1, which is this one. And since we assign the 1, a high, into this address, and F is going to output address 1, we have still is 1. And this one is 0, 1, 0. 0, 1, 0 is 2, right? So we outputted W here. So in this case, W is 0. And without any invert, 0 pass to the output, so we have output at 0 here, and so on. So this one we have 1, 1, 1, and but the W is still 0, and so 1, 1, 1 is address 7, and we assigned W naught into address 7 to pass through F, and W0 invert is 1 here. So following this logic, we can then complete the waveform. And as you can see here, this waveform is not finished. So we can, on the bottom left corner, we can type run and 1000. So it will run more simulation. Okay, so let's do the next problem, which is, I believe, is your homework problem. I'm not supposed to help with your homework problem, right? But I think that will be a good practice. Okay, this one. Okay, so before I begin, I want to make sure that your homework is for this one is due already, because I know your professor said that you are not allowed to get any help, right? It's still active? Oh no. Okay, so let's not do this one. Let's do a similar problem, but not this one. This. So let's say file, new project. I'm not sure if you're going to code in the future, but you can follow this, and this might be helpful. So well, this is an empty view, and we can click on new source, and then we can put Verilog module. Let's say this is test 10. And let's say we have an input of A. Yeah, input of A and output of, let's say, Y. Maybe test. Well, I'm just following the homework here. Let's say X. And C. This is our output. So first, like I mentioned before, the always block is going to loop through what's inside its body whenever the parameter, the variable inside parameter changes, right? So let's say A. So, and we can begin here. So if we assign X as 3 and 0, 0, 0. Now this function here is saying that the input X is 3-bit binary. This is binary. This is binary and 3-bit, so we have 0, 0, 0 here. You want me to help with your homework? Okay, no, I cannot do that. So then the next function is, let's say X equals to X 1. So this function is saying that you're shifting the value of X to the left for 1 bit only. What it means is that if X equals to 3-bit 0, 0, 1, and this function one is going to tell you to shift the value of x to the left 1 bit. So your new x will become 3-bit 0, 1, 0. Does this make sense? So what if we want to shift it to the right? Right. So if we want to shift this to the right, then we can just say s shift to the right by 1 bit. So we will go back to x equal to 3-bit 0, 0, 1 again. And if we want to shift left 2-bit, what do we do? Right. So x shift left 2, and what would the new x be? Right, so 1, 0, 0. So what happens if I shift left again by 1 bit? So yes, I would that was what I thought before I started Verilog. Yes, but it's going to be 0, 0, 0. The 1 disappear. So there's no 1 anymore. So now move on to the next function. So what if I put x equals to like 8? Let's say 4-bit. And what if I put the x here? So x in Kmap symbolize don't cares, right? So for x equals to 4-bit don't cares, it's equivalent to 4-bit 1, 2, 3, 4. The don't cares. Don't cares means that it's neither 0 or nor 1. And does that make sense? Any question? Okay, so yes, there's another function, it's C. C symbolizes high impedance, so that means you will never get any values. You will just get C. It's neither 0 nor 1, but it's just C. Just in case that's on the test. And next one. And I'm sure I talked about for loops already, right? For, let's say, I equals to 0, I equals to 15. I equals to I plus 1. And don't forget the begin here and end. So if we want to use I here, we have to assign a register dedicated for I. Register for I. Say this might be 30. I'm not so sure about this because it's 3-bit. So I. So what this function do is that it's going to loop from 0. Well, this is less than. It can be less than or equal to 15. And I less than equal to 15. So at first I equals to 0, and I is going to plus 1 after each time it goes back here until 15, and then it will stop. For if statement, if we are not assigning values to the variable, we have to use double equal sign to compare it. And for less than, we're just going to put less than, and less than equal will be less than equal, greater than will be greater than equal. And if we're testing whether A is equals to end when A ended with B, and if they're equal, if they're output at 1, we have to put A and end B. So let's say let me see. So let's say A equals to 3-bit 0, 1, 0, and B equals to 3-bit 0, 0, 0. And we want to compare whether A ended with B will equal to 1. In this case, it's not right, so we can write if statement, and instead of A and B, because A and B will give you a value of 0, 0, 0. So this first the same MSB bit ended with each other, it will be 0, and 1 ended with 0 will be 0, and 0 ended with 0 will be 0. So if we're testing whether A and it with B will be 1, then we have to put A and B. Does that make sense? Okay. And please let me know if you have any question. So we have the same thing is for or. And let's start with A or B. We have 0, 1, 0, 0, 0, 0. If we OR A and B together, what value will I get? Right, 0, 1, 0. So if we're testing this, we have to put A or B. Right. And let's say we have 0, 1, 1 and 0, 1, 0. So this is A, this is B. What if I end A and B together? What's the value? right, 0, 1, 0, right? So yeah, I guess that covers everything. And if you have any more questions, please ask now. Is this helpful? I hope it is. Okay. Anyone? Okay, so I got a question about okay, Kmap. Oh, the grouping. And you're trying to find the function. Hopefully that makes sense. So I'm going to use an example from the Wikipedia because it's really to the point. And I'm going to go over the decoder later. And let's say, where is, okay, Kmap. Maybe I should just show you the web page because I think it's really clear. Explain it. Can everyone see this? Okay, so this is our given function here. This is sum of minterm for 8, 10, 11, 12, and 15. And the don't care is here. So when doing the Kmap, we always want to include the don't cares. So just in case, we can use the don't cares to simplify it. So we set the don't cares to 1. And in this case, they're set to x first. So we first write the function, turn the function into the truth table. So from 0 to 15. So as you can see, from 4, 8, 4 is 1, 8 is 1, and 9 is don't care, so on. So after this step, we want to group the number of ones together because this is just easier to see, because we want to find the one bit that is changing. So in this case, M8, as you can see here, M9 is your don't care. We include it into the function. So as you can see, 100 stay the same as 100 here, and the only bit that's not changing is this one, right? That's changing is this one. So we can then simplify this. M89 is 100 and dash. And M4, we want to check all the possible values. So M8 has one bit that is changing with M9, and M8 with M10 is also changing this bit here. So as you can see, we have this. And next part will be M8 compare it with M12. So we can see this bit is changing. So we can find 1-00. And after comparing all the value for M8, we can then move on to M9. So M9, we can see it shares only one changing bit with M11. So which we can then group them together. 10-1. And then we follow the same procedure by checking all the terms to see whether they share one changing bit. So from the size2 implicants, we can then simplify it further. I mean, by simplifying, I mean grouping them. So we see n, 4, and 12, and compare with the group here. We can see this doesn't share any changing bit with others, right? And how about this one? This one is going to share one changing bit with M10. Do you notice that there's a dash on the first bit, and then there's one changing bit on the second bit, and the rest stay the same. So we can group M9 and 8, 9 with M10 and 11. And then we compare all the possible value. So the next part will be the prime implicant chart, as you can see here. And then we want to get this. And then, so we notice that we are missing 4 and 12. We're missing 4 from these 3. So we want to include n, 4, and 12 in the prime implicant chart. So as you can see, this. And then we find 8, 9, 10, 11. The reason we are not using the term here is because we already have all the values included in this term. So m, 8, 9, 10, 11 is listed here, and so on. M, 8, 10, 12, 14, this part, and the last part is this one. So, and we can see that n, 4, 12 covers 4 and 12, minterms for 4 and 12, and 8, 9, 10, 11 is going to cover 8, 10, 11, and then in this case we got rid of 9 because I will explain it later. So then 8, 10, 12, 14, we already covered that. 8, 10, 12, 14 is missing as well. So 10, 11, 14, and 15. So 10, 11, 14, and 15, which is this one here. Any questions so far? And then we can move on to this part. No questions? So we know that M412 is going to equal to this term here, right? So we put a dash 1, 0, 0 here. And how about this one? And 8, 9, 10, 11 is equal to 1, 0, dash dash. So we put it here, and then we do the rest for others. So now we can move on to the next part. Let me check the message here. So we know that we have to have M, 4, and 12 if we want to cover the minterm 4. So we have to include B, C naught, D naught, which is this part here. A is dash, so it can be either 0 or 1, so it doesn't matter. So we write down the minterm here. And then how about the next one? We will have this one here. This will be A, B naught, A, B naught, like in this case. And then the next one will be M, 10, 11, 14, 15, and it's going to be AC. And the reason that we're not including this one is because if we use M412, it covers 412. So let me see if I can draw on this. Let me take a picture of this. Okay. And then we know if we select this minterm here, we can already cover 4. 4 is gone. And then 12 is gone as well. If we choose this minterm here, which is A, B, B naught, then these 3 terms are gone. And the only one that you see here that's not covered yet is this one, right? So we can use, we have to write down this minterm as A and C. And there's other ways to do this, or we can use other minterms. And if we use AD naught first, we know all the 3, 8, 10, 12 are covered. And then what's missing is this term, because we need the 4. And this term, because we need a B naught. No, we don't need a B naught. No, sorry about this. We don't need this term, because if we choose this term, then it covers all of them already. So we choose this term instead of this one, which is AC. AD naught or AC. Is there any question for this? All clear? Okay, that's great. Okay, so let's go back to do the decoder for PC. Yeah, let's start a new one. For the decoder circuit, we know the definition for the decoder is, let's say we have X, Y as our input. Then we know we will have four outputs, right? So F3, F2, F1, and F0. Because according to the definition of the decoder, this is how it is. And start from 0, 0, 0, 1, 1, 0, and 1, 1. So in order to fill out the truth table, we know the definition of the decoder when XY is 0, 0. So it's 0 and 1. This is 0, 1, 2, 3. And let's say this is your F0, F1, F2, and F3. When XY are 0, 0, that means we want the address at 0 to output a 1, and the rest will be 0. And likewise for if x is 0 and y is 1, we want the address at 1 to output a 1, and the rest will be 0. And then we do the same thing for all the other potential inputs. So as you can see here, we can then write the function for this output here at address 0 as x0, y0. Because when x is 0, y is 0, 0 inverse ended with 0 inverse is equals to 1. So for this output, what would it be? Can someone tell me? This one will be x not y. Yes, that's correct. So if we put x as 0 and y as 1, then we 0 inverse ended with 1. This will be 1. And we can go back to check this one. 0 inverse ended with 1 inverse. This will be 0, right? So how about the output at address 2? X, Y not. Correct. I see that you're already using the Verilog function there. And the last one will be XY, correct. So is there any more questions regarding the decoder? Okay, so let's say we want to utilize the decoder and say we have to realize the function as f equals to x naught y naught ended with x y naught. Then we can simply connect the output of this one to this one and this one to this one. So this will be your f. And same thing for the OR gate, which is x naught y naught or x y naught. So we can do the same thing, right? Connect it, and this will be your f. Any question? All good? Okay, let's see. Implement the following logic circuit with 3 by 8 decoder. Oh, I see. Okay. So by applying this concept here, we can then do the more complicated problem, right? Which is, let's say, paste. What? Sorry about this. Give me a second. Paste. Okay, so we're given a function of, make this more visible. We're given a function of p and v, w, x, y, z equals to w x naught y, or v naught z naught, or w x naught y naught, or vz. And q w x y z will equal to w x naught y naught plus w y z. Okay, so as you can see here, we have four variables, right? So how are we going to solve this problem using the 3x8 decoders? So let's say we draw the decoder first. We have 3 inputs, 0, 1, 2, and 8 outputs, right? 2, 3, 5, 6, 7. And let's choose a random 3 value. Let's say x, y, z as our input. So this will be z, y, no, sorry, because we want the x to stay as MSB, x, y, z. So the output at this address will be x naught, y naught, z naught, x naught, y naught, z, x naught, y, z naught. How about for 3? What's the output at 3? Yes, x naught, y, z, and x, y, z, y naught, z naught, x, y naught, z, x, y, y, z naught, and x, y, z, right? But the problem here we have here is we're missing like w and v, right? So what do we do? The problem is also say that we can use NAND gates. So we can do w as input here, w as input, and let's look at q first. So how do we do this problem? We know w x naught y naught can be expanded with z or z naught. So we will get w x naught y naught z or w x naught y naught z naught, right? So how do we convert this to a NAND configuration? We can double invert applying what we learned from the previous review. So this will be, sorry. We can make this as W x naught y naught C ended with W x naught y naught C. And don't forget the one we didn't do. So we know that x naught y naught C is here. So what do we do with this term? And W as input here, and a NAND gate. We will connect the output of the decoder for the x naught y naught C to the NAND gate here. And W here. Right? Does this part make sense? Okay, so then how about this term? We have W x naught y naught C. Wait, am I missing something? Oh, sorry, so this is a Z naught. I missed it. This is C naught. Sorry, my PC is really slow now. Oh no, I lost it. Oh, this one. Okay, great. So we want to connect use another NAND gate here. And connect W with this NAND gate. And since the term we're missing here is x naught, y naught, c naught, we can then pick this output from the decoder and connect to the NAND gate. And the last part will be the two input NAND gate for the entire term, which is like this. So looking back at the function, this will be your Q output. Does that make sense? Okay, yes. How about proceed? Okay, so let's do P now. For P, we just add another variable, right? And do this configuration. So for P, we have, let's see if I can erase this. Well, okay, great. we know that for p function, we're missing from the input v and w. So p equals to also equals to not, right? So w x naught y plus b naught c naught plus w x naught y naught plus bz. Now, in order to apply the double invert first, we have to get this term to its most complicated term, which is w x naught y, and let me think about this. Maybe there's an easier way. Maybe we only need w and x. No, we only need x and y, because this is the part we cannot change. So we have to put the term in x, y, z form. So b naught, what happened? So b naught, c naught, we have to expand it with x naught or x, and this will become Sorry, I know that this review is supposed to end at 9, but running late. It's not letting me erase this. I have no idea why. So we will get b naught x naught c naught, or b naught x naught, b naught x. Okay, b naught x c naught, and then expand this further. So we will get c naught b naught x naught, and then we can skip the process and do it y c naught, or b naught x naught y naught and c naught. And for this term, this belongs to this one, and this term we will get b naught x y naught c naught, or b naught x y c naught. And since we have completed this term, so we got a function p as w x naught y, or b naught x naught y c naught, or b naught x naught y naught c naught, or b naught x c naught x y c naught. And I erase this. Okay, so then we're looking at this term right now. So or wx naught y naught or ez. So we know that this term here is missing. It is missing z, right? And this term here is also missing z. This term is missing xy. So then we do the same for BC to expand it into XYZ form, and then we do the same for WX naught Y to get the XYZ form. And after, we will be able to do the NAND configuration. Do you want me to do this? I can go through this if you want, but I don't want to take too much of your time. Okay, so how about Percy? Okay. Yeah, but I can do it if you want. Just if you're willing to stay here longer. Is there any more questions? Thank you, Coleman. Greatly appreciate your comment. Thank you. Anyone has any more question? Love Batansh, thanks. Thank you, Nick, and thank you, Hadi. So if no one has any more question, I want to give you the last slide here, which is final. Yeah. Good night, Howdy. Thank you so much for coming. Thanks, everyone. Good luck. Good night, Coleman. Yes, please switch.